라고 우리 학생들이 포리어 트랜스폼을 안 배웠다고 하니까. 그리고 이거 하고 있었지. Alright, so let's talk about this. Okay, so we were right here the other time. So we have the continuous waveform comes in as a signal and noise as a random process. What was the random process? Random variable is a function, right, from sample space to a number space. And random process time parameterized by t is just a random variable for each time t, right? So if you have a continuous process, basically each instance is a random variable, another time instance, another random variable. Then we want to know if these two random variables are dependent or not. But in as far as concerning this class, we are not going to consider when there are some correlations or some dependency, right? Why was that? Because dealing with the white noise is the most difficult thing, right? If you are able to utilize some connection between the two, then you can use it and reduce the power of the noise, right? So it's an easier problem, right? So we want to consider the most fundamental one. That is what the textbook is called wide sense stationary white noise. White noise makes this uncorrelationness. Okay, these two random variables are not related with each other. Okay, but that happens only when this random process is just as it is. But when we do some filtering onto it, then we will start to see some correlation. Okay. That we will talk about it after we talk about the sampling theorem, maybe. And the figure on the right makes sense, right? If you have a signal, basically this is the signal, and then Shannon's theorem says you could have a message set size of capital M, and then this M here is an index, so that if small m is equal to 1, you are talking about the first message. M is equal to 2, second message, out of this message set. So that's what it is. And then we are using continuous waveform. Why we are using continuous waveform? Why don't we just send vectors? Because in reality, the world is analog world, right? In order to send the digital information, you have to interface with the analog waveform. Voltages and currents are continuous waveforms, right? And the electromagnetic waves are also continuous waveforms. So we have to use them to deliver our message from transmitter to the receiver. Okay? Over the internet, over the, let's say, wireless channels, and so on. Okay? And then this noise added to the signal is also wireless. But when we design this communication system, we may use this vector representation, right? Why are we doing that? Because if we do this, what is the benefit? Basically, we can find the optimum system, right? And then optimum here is in the sense that the amount of information sent through this channel is maximized, or make it robust using channel error correction code, and so on. So there is a benefit of using this type of system. Okay, so that is the reason that we are doing. And then here, this psi 1 to all the way up to n implies these basis vectors or basis waveforms, right? And then they are what? They are orthogonal to each other, right? And then we use this to span the n-dimensional signal space. Okay, and then you send this signal over the channel, and you receive. And then probably today we are going to talk about how we are going to receive it, right? In order to maximize the benefit. So here are some methods to send the waveform, and then which basis and the signal set we are going to choose depends on your resource, okay? And then depends on what you want, okay? First thing is a time division waveforms. We can use time divided messages. So, for example, let's say I use 3 bases like this. Divide the time three ways like this, and then I use a waveform that looks something like this. Second one, use something like that. Third one, something like this. Okay. So I call this psi 1t, psi 2t, psi 3t. Are they orthogonal to each other or not? The time. Well, what is the orthogonality? Inner product, right? So if I take the inner product of the two, is it equal to 0 or not? It is 0. So multiply this number with that one 0. This with 0. So inner product is 0. Okay. Then what type of signal can I span using these 3? What type of signals can I span with these 3 basis vectors? So I'm starting to use waveforms and vectors are the same manner, right? So what type of signal? What is the one signal that you can span using this? Let me give you an example. Maybe I draw it right here. Can I make this a signal? Let's say here is one, the height is one, all of them. Height is one, right? Only the position change. Can I make up this signal? So I'll call this signal number 1. Can I do this or not? Any arbitrary height. Possible, right? So for example, if this height is H1 and then H2, H3, how can you do that? H1 times psi 1, right? Plus H2 psi 2 t, H3 psi 3 t. That is this waveform, right? And then the actual number I might choose is 3. Maybe this one is 2, and this one is -1. I can do that. Right? Just plug in those numbers right here. Then I have this waveform. Okay. Now, can I? So this is possible. Yes. Now, can I make some signal like this? Like this? Can I do this? Is this possible? No. Yeah, no. Huh? Yeah. So you might try, right? You might try with that one. If you do that, you would probably get what? You would probably get something closer, like. Okay. This yellow is the one that can be spanned by these 3 functions, but not exact one, right? So there will be some discrepancies. But what happens if I inject these into the 3 signal vectors I have? So take the inner product and represent. What happens? Then it is possible. And then there will be some discrepancies, but we can treat it as out of space signals or noise. We can do that too. So that is a time division manner of designing system. So I divide the time this manner. I can do that. But this is not the only way. Maybe so I'm telling you the most simple one. So this is a time division signal. How about now we do this in the frequency domain? So instead of time domain, I do with the frequency axis. And this is a frequency function now. Frequency. Same story, right? Same story. I design the system in time domain. I can design the system in frequency domain. Okay? Now, this is too simple, Professor. Right? Can you give me more complex example, right? You can do that? In such a case, probably you have to use some pseudo-random sequence, pseudo-random value, pseudo-random sequence, Q-U-E-N-C, pseudo-random sequence. For example, I generate these ones and zeros, or ones and minus one, randomly. Okay? So I use a basic waveform like that, but I will modulate it with a pseudo-random number. So here, pseudo-random number here is you have learned the Bernoulli random variable, right? The other time. I choose these numbers randomly. For example, like this. So I just, since the height is the same, I'll just say that plus or minus, plus, minus, plus, minus, minus, plus, 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 things like that. Some long sequence. Plus, minus, minus, plus, minus, minus, minus 3 times, plus, plus, plus 3 times. So I use this type of waveform. I call this psi1. Okay? And then I also create the psi2 and also pseudo-random manner. Just ask the computer to give me pseudo-random sequence of binary numbers, right? Then it will give you minus, plus, plus, minus, minus, minus. 이 숫자는 같아야지. 너무 자유도가 높네. 하나, 둘, 셋, 넷, 다섯. 12개구나. 마이너스, 플러스, 플러스, 마이너스, 플러스, 마이너스, like that. Okay? Then I can create a waveform. So minus, plus, plus, minus, 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 plus, plus, minus, plus, minus. Like that. Are these two orthogonal? You have to do it, right? You have to do a calculation. So in order to calculate it, what is going to be? Plus, minus is plus, right? When you multiply, right? Plus 1 multiply with minus 1 is minus 1. Oh, minus 1. So minus, and minus plus is minus, right? Plus plus is plus. Minus minus is plus, right? Minus minus plus. Plus minus You know what I'm doing, right? What is going to be the addition of these numbers? So let's say C1, C2, C12. What if you add these numbers from I1 to 12 and divide it by the number of addition, what do you think this number will go? With a large n. Increase 12 by 1000, for example. 아, 이거 또 꺼지는구나. 이거 칠판을 너무 쓰면 안 되는구나. 꺼지면 키기가 어려우니까. So what would happen if we increase this pseudo-random length of the pseudo-random sequence? What if I change this to, let's say, n, averaged by n? Where do you think this number converge? 0. What do we call this? Law of large numbers, right? Law of large numbers. So if you add random numbers n times, this will go to 0, right? And then if we obtain this, what have we achieved? What is the inner product between the two? It's going to be 0, right? Then I can create waveform that are orthogonal to each other like this way. So this is something called code division. This is something called code division. Okay, so code division modulation. So we modulate our signal. So when I send this one, this is bit 1. When this signal, this is bit 0. Right? That type of encoding can be done. Okay. So what is the downside of this choice? Now, if we understand this, what would be the disadvantage of using this type of signaling? Am I utilizing the resource efficiently or not? What is the resource here? Time, right? Time access. I use this channel 12 times, but I'm sending only how many bits? I use the channel 12 times. I am sending how many bits? 1 bit. Oh, this is 1/12 rate coding. In this case, when I use channel once, I'm sending 1 bit. But in that case, I'm sending 1 bit using 12 channels. Okay? So we have to utilize this with our purpose. And then in such a case, I can increase this type of pseudo-random sequence to be, let's say, all the way up to 4. So in such a case, I am sending 2 bits per sequence, and so on. So they are using this code division sequence in wireless communications. Okay? And in the deep space communications, what are we short of? When you send these messages to version number 2, what is the dearest resource? What are we lack of? Transmit power. The reception sensitivity will be very, very small. In such a case, you have to do what? Loss of coding, loss of redundancies. This is one way of doing redundancies, right? Even though it is not a good coding. So that is what we mean by code division. So we can divide time axis, we can divide frequency axis, we can divide messages according to codes like that, and so on. Okay? So these 3 are the most famous examples. Okay? All right. Do you have any question on this? Okay, and then here is the picture way of representing it, and basically in this case, signal x1 is a vector 1 and 0, right? X2 is 0 and 1, and here is x3, which is minus 1 and 0, and x4 is 0 and minus 1. So now I can ask you, what is the dimensionality of this signal set? What is the dimensionality? I have 4 signals. Do I have a dimensionality of 4? No, because this and that are same in the same space, single line, right? And then this one and that, single line. But this and that are orthogonal to each other. Okay, so the dimension is 2, so the length of the vector is 2. Okay. All right. Signal space representation. We may now attempt to draw signals in the signal space. So in this particular example, I can draw these vectors in the vector space, right? Then I will have 4 points, right? 1, 0, 0, 1. Maybe we can draw, since this is easy. So what if we draw, what is that going to look like? I have a 2-dimensional signal, so I represent this is the psi 1 direction. This one is psi 2 direction, right? And then this one says 1, 0, right? So 1, minus 1, 1, minus 1, 1, minus 1. So I have 4 points. No, not this way. These 4 points, right? All right, using that notation, 1, 0, which is this one, x1. x2 is 0, 1. 0, 1. So this is x2. Right? And then minus 1, 0 is x3. This is x4. Yeah. Are you okay? Can I create another constellation? So this is called constellation. When you read the textbook, this is called a constellation. Now, can I create same energy signal, but in different form? Can I change the signal this way? Or not? Let's call this degree 45 degree. Can we do that or not? So I'll say this signal set to be set number 2. First one to be set number 1. Are they going to perform differently or perform the same? Why do we have to concern? What is the one that we have to care in terms of probability of making errors at the receiver? 내가 너무 빨리 나갔나? 가만 있어봐. 그러면 뭐 so let's think about this constellation set number 2. So what is this one going to be? What is this value right here? Vector right here? You know? 루트 2. 그 코사인을 사용하자고. 각도 있으니까. 코사인 파이 오버 4. 파이 오버 4가 45도 맞지? 그 다음에 이건 뭐지? y-axis 사인 파이 오버 4. 그지? 요것도 45 하지 말고. 그죠? 그러면 요거 나왔으니까 다 나오죠? 그러면 얘는 뭐죠? 마이너스 코사인 파이 오버 4. sin pi over 4. 이렇게 해서 4포인트 나오죠. 그러면 요 시그널 셋이 다 나오지. 요거 코사인 파이 오버 4, 사인 파이 오버 4 이렇게 해서 4개 다 적을 수 있잖아요. So this is signal set number 2 or signal set triangle. Then now I am trying to ask you. Now I want to consider probability of making error for signal set, the original signal set. Let's call it 1. Probability of making error for the triangle set. Are they going to be same or different? Why same? Same distances. Right? So when we consider making errors, basically, you send this one, there is going to be some scatter plot around this point. When you send this one, you have a scatter plot around this point. If these two overlaps, there will be a source of errors, right? But if we rotate this by 45 degrees, would the geometry change in terms of distance? No, no change. So the performance will be exactly the same. Now, in order to use signal set number 1, you spend, let's say, 1 watt of power, 1 watt. So distance will give you, right? And in order to use this signal set, is the transmitter power different or the same? Same, because the lengths are the same, right? Signal length is the energy and the power, right? Length square, actually. Length square is a signal or power. How do you divide signal, energy signal versus power signal? Like I told you, we have to use the finite length vectors, right? So if the cosine function that we are talking about, this is what? Power signal, right? Because if you integrate the square of cosine, it is going to be infinite, right? So we have to do it for single period, power signal, right? So based on what your choice is, like in terms of basis, it could be power or it could be energy, but same thing is you just take the square of the length, it is energy or power, okay? All right, anyway, so we are using same power and then we obtain the same protection against the noise, okay? That's it. All right, so these are the, the things that we are using this sample space, signal space representation. And we may attempt to draw signals in the signal space we just have done, right? Most simple one. Can you compare M and N, right? Can you compare M and N? N is the signal dimension. M is the number of signals. What type of relation do we have? Yeah. M should be bigger or equal to N, right? All right, that's good. We are making progress. Now this is a little more involved example. Now we need to find the dimensionality of this signal set, right? First off, we have to find the basis set, okay? And then obtain the vector representation. And then draw signal space plot, compute the distances between signals, right? We can do that, right? Okay, what are the bases here? What is the most simple basis? What do you think is the dimensionality of this set?
4 dimension.
Dimension 4. Why do you think so?
we face a dimension like first one and second.
You think that is the only way that you will have a linearly independent vectors, right? That's the only way, right? Because this is exactly divided into 4 different time intervals, right? There is no way, without using 4 time interval vectors, you can span these vectors, right? There is no way, right? So that's basically it, right? And then once you have found the basis, right, what do you have to do? You take inner product with the basis vector, right? That is going to be the coefficient. You have to find these things, right? And then if you take the square of each coefficient, add them all up, it's going to be the energy of the vector or power of the vector. And then if you want to find out the length of this vector, you just need to take the square root. Okay? So that's what you need to do. And then you can do that. Rest of them is just the arithmetics. Okay? And then once you have found these 4 points, what does it matter is the distance between them. Right? So for example, let me redraw this. Let me redraw this. Okay, the original one. Right? Now here, what are the noise vectors that we have to worry about in this case, as far as concerning the detection of signals? So here, this is the origin, and then I have some vectors perpendicular to this, or some other high-dimensional noises. Do I have to worry about them? Why not? Because if I inner product with these 2 basis vector, they are going to be all going to 0, right? So I don't have to worry about it. So here, what are the 2 noise vectors? Basically, noise in this direction, noise in that direction. Or I can rotate this any angle that I want. And then because this noise is same strength in any direction, I can just change the basis, and then I can draw 2 axes any way I like. Okay. For example, I can rotate the axis for noise this way. 2 axes like that, and then I can talk about this event. I sent this vector, this one sent. I can ask the question, what is the probability that I have to give the name. So this name is x1, right? I sent x1, okay? Maybe conditional probability I haven't taught, right? So sent x1, and this is x2. What is the probability that you are going to be confused with x2? So let's say x1 sent. What is the probability that you will be confused with x2? That is the case. You sent this one, but the received signal land right here, right? Then which one is closer? Is this closer to that one or this one? Closer to that one. Then you will probably decide, aha, this one, if you received this one, maybe x2 was sent, right? So that's it, okay? That's the message that we are getting. So In order to do this, basically what we need to do is we need to find the decision boundaries. Decision boundaries. So if received signal land in this region, I'm going to say X2 was sent. And then if this one was sent, I'm going to, if I receive any receive the signal in this region, then I'm going to say this one was sent. Okay? So this type of decision boundary, decision cell can be designed. But in this case, this is straightforward, right? Because this has a symmetry in it. So we can just draw decision boundary like that. Okay? Now, what if, this is a toy example, what if we increase the dimension of the signal set? Not only the 2-dimensional, but 3-dimension. We can draw only up to 3 dimensions, right? But in the vector space, we can deal with a 1,000-dimension signal, right? In such a case, do you think drawing a decision boundary is easy or difficult? There are too many combinations that you have to think about. It is generally very difficult, okay? So that's all. But I'm just giving you some points to think about, right? And now the big picture view is this. So if this M is the size of the signal set, then the number of bits that you are sending is log 2M. For example, M is 8. 2 to the power of 3 is 8. So you are sending 3 bits per single channel use. 3 bits per single waveform transmitted. Okay. So and then how are you going to select the messages? How you are going to select this SM? So S here represents a waveform. M is the one that we have to select, right? Index. So what is this index M? If size of the signal set is 8, in your sample space, I have a 8 object. I will randomly select one ball out of this pulse, right? And then I will assign 1/8, the probability of 1/8, right, for each one. Then I am sending this message with the probability of 1/8. So I can make use of this random variable. Then basically M is a random variable. And this random variable basically maps from where to where? Sample space to this vector space or signal set space, right? Here, you select one object, then you are selecting one waveform to send, okay? Then that is what this box is telling you. And then you send this waveform over the channel, which is a physical world. And then there will be noise added to it. So what you receive is a noisy version of what was transmitted. Okay? And then you have to do demodulation. Okay? Demodulation. You have to do something at the receiver, right? In order to bring this index back. Okay? Index back so that you can make a decision. If you send the index 1, the first signal in the set, you should be able to recover index to be 1, right? Not 2 or 3 or other index, right? So that is your objective. And then we will call it decision variable, okay? The digital number that you create or the index that you create is going to be compared with what was the transmitted index, okay? It better be the same. If these two are not the same, probability of error is not equal to 0. Okay. And then what are you going to do with the demodulation? How can you bring back down to the index level in our particular example? What do you need to do? 그게 이제 디시전 하는 거고, 그리고 그거를 하려 그러면은 일단은 피지컬 웨이브폼을 어떻게 해야 돼? 지금 여기 받은 얘는 피지컬 웨이브폼이잖아. 그 피지컬 웨이브폼을 우리가 지금 다룰 수 있는 숫자 레벨로 바꾸려 그러면 어떻게 해야 돼? 저건 트랜스미터에서 저렇게 한 거잖아. 그지? 근데 여기서 레프레젠트를 한 게 여기서 어떤 포인트로 갔어. 매핑이 됐어. 얘를 레프레젠트 하는 피지컬 웨이브폼이 RT잖아. 그지? RT잖아. RT를 벡터 스페이스의 포인트로 바꿔주려고 그러면 뭘 해야 돼? 그 얘기지. What do you need to do to bring RT to this signal space representation? So we can call it R, vector R, right? In order to specify vector R, what do you need to do? You need the coefficient for first axis. You need the coefficient for second axis. Right? Then you can, the waveform is right here. How do you obtain R1 and R2? That's what my question is.
By inner product.
Yeah, inner product. So for example, R1, inner product RT with psi 1t. Right? So R1, how do you obtain R1? R1 is you have a basis vector psi 1t. You inner product that with RT, the voltage waveform that you received at your antenna output, right? And then add them all up. Okay? Then R1. Use psi 2 here to get R2. Then you get it. And this is the optimal one. Okay? Now, these days, communication engineering system uses deep neural network as well as a receiver. So instead of using this type of demodulation, you just need to learn the pattern through training, and then you can utilize the deep neural network to make a decision as well. But the most optimal solution is this. No matter how many deep layers that you use, you cannot perform better than this. Okay. All right. So that's what demodulation is. Okay. Demodulation. So modulation, demodulation. Modulation in the wider sense is to interface the channel. So you have to make a physical waveform to send your digital message, right? And then at the receiver, you have this physical signal you bring down to the vector space. That's what we call demodulation. Okay. So choose a set of m distinct signal waveforms. So that's the design part. When you choose m signals, this is the optimal way. I have told you why, because this has a distance structure that is like that. And let me ask you a question. So here the signal set size is m is equal to 4, right? Now I design my system still the same, but here I design my system. Let's see. I use these 4 signal points. So my constellation look like this. This is centered around 1, 0 rather than 0, 0. Which one is better design? And why?
But does that linear?
What did you say? Is this linear?
I
So my question is, which one better? Which one? This way or that way? 어떻게 더 좋은 거야? 왜 그런 거야? 이 질문이지.
because
내가 그러면은 질문을 브레이크 해줄게. probability error가 얘랑 달라? 에?
maybe
probability of error를 결정하는 게 뭐야? 디스턴스 스트럭처라잖아. 이 네 포인트 간에. 그지? 내가 얘 보냈는데 얘로 헷갈릴 확률, 얘로 헷갈릴 확률, 얘로 헷갈릴 확률. 그게 달라졌어? 안 달라졌지. 그러면 똑같잖아. probability of error는 똑같네. 그지? 디스턴스가 똑같기 때문에. 그지? 근데 우리가 통신 시스템에서 지금 생각하려고 하는 거는 뭐가 있지? resource. 그지? 뭐가 resource지? 벡터 에너지, 파워. 얼마만큼의 신호의 세기로 보내느냐, 동일한 probability of error를 얻느냐, 그 얘기잖아. 그지? 근데 디스턴스가 똑같대. 그러면 probability of error는 두 셋이 똑같아요. 그죠? 근데 누가 더 파워를 많이 써? 오른쪽이 많겠지. 얘는 에버리지 에너지가 1이지. 그지? 얘는 얘 하나 보내는데도 2의 제곱이면 4잖아. 근데 4개를 다 더하면 더 많아지겠지. 그지? 그러면 동일한 probability of error, 동일한 양의 정보를 보내는데 더 많은 에너지를 쓰잖아. 그지? 그러니까 얘가 요 세 가지 면을 봤을 때 더 안 좋은 거지. 그지? Get it? 그지? 그게 시그널 스페이스 디자인이야. 그지? 어떻게 하면 작은 에너지를 쓰면서, 최소 에너지를 쓰면서 가장 많은 정보를 에러 없이 보내느냐, 이거 얘기하는 거잖아. 그치? 그러면 이거에 대한 포인트는 전달이 된 것 같고, dimensionality 다 전달됐지. 그래서 modulation is implied mapping rule. 그죠? mapping rule이지. sample space에서 signal space로 이런 거. 그지? 그 다음에 waveform space에서 vector space로 옮긴 다음에 index 화하는 거. 그건 decision 하는 거. 그지? which takes a string of k bits. 그지? k는 log to m. 그지? 8이면 m이 8이면 3bit, m이 16이면 4bit, m이 1024면 10bit, 그지? 보낸다. 그러면 1024 시그널 포인트를 어떻게 디자인할 것인가 이런 거 생각하는 거야. 쉽게 얘기해서. And then transmits the corresponding signal over the channel. 그지? 다 펑션으로 이루어진 거야. 그지? 그러면 이제 우리 학생들이 파이썬으로 코드를 짤 수 있어. 내가 신호를 보내려고 해. 어떻게 보내야 돼? 근데 볼테이지 웨이폼 같은 거 생각할 필요 있나? 없다 이거지. 일단 시그널 스페이스로 레프레젠테이션 해놓고 시그널 스페이스로 디자인을 한 다음에 피지컬 인터페이스 뭘로 할 것인가? 타임 디비전으로 할 것인가? 코드 디비전으로 할 것인가? 정하면 끝이야. 그게 시스템의 통신 시스템 디자이너의 일이야. 오케이? 그 다음에 멀티플 안테나를 쓰면 어떻게 돼? 매트릭스가 보내죠. 매트릭스. 벡터가 보내지는 게 아니라 매트릭스. 여러 개의 안테나를 여기 없지. 우리 그 와이파이 액세스 포인트 보면 안테나가 4개 달린 것도 있고 그러잖아. 그러면 한 번 채널을 사용하는데 4개의 시그널이 간다고. 웨이폼이. 그러면 받으면 뭐야? 4 received sample을 받지. 그리고 길이로 봤을 때 하나의 코드워드니까 매트릭스지. 그래서 매트릭스를 보내고 매트릭스를 받아. 그러니까 다 수학이야. 그러면 매트릭스 그 엔지니어링, 그다음 매트릭스 어널리시스, 매트릭스에 대해서 디시전 티오리 이렇게 해야 되는 거지. 그거는 뭐 무선 통신 채널 그거 내 렉처 보면 조금 나오는데 그거 보면 되고 이 학기에서는 그거 안 할 거야. 매트릭스까지 가장 기본적인 것만 할 거야. 그래서 demodulation is to imply the process of converting the analog waveform into string of digits, okay, or the test variable. 요 test variable을 요거라고 해. 그 바로 앞단에 있는 거 숫자. 그지? 혹은 벡터. 그걸 가지고 인덱스 M 찾는 거지. 트랜스미트된 인덱스. 그래서 여기서 우리의 그 the decision device makes the final decision. 오케이? 그러면 decision device라는 게 사실은 뭐야? 컴퓨터 프로그램이지. 그지? 요 피지컬 채널 인터페이스 하는 데만 서큐트과 그다음에 뭐 컴퓨터가 인볼브가 되고 그 나머지는 다 컴퓨터에서 돌아가는 프로그램이야. 소프트웨어. 그치? 알고리즘 다 프로그램으로 짠다. 그치? 그래서 그렇게 해서 된다. 그래서 지금 커뮤니케이션 시스템이 이제 그렇게 되는 거지. 그래서 minimize the probability of error. 그지? While minimizing the transmit power. 그지? 혹은 동일한 transmit power를 썼을 때 minimize 하는 거. 그런 거. 그래서 probability of error는 내가 decision한 m 프라임이 실제로 보내진 m과 같으면 에러가 없는 거고 다르면 에러지. 오케이 됐죠? 오케이 그러면 옵티멈 디시전 룰이 뭡니까? 이제 이거를 한 거야. 근데 뭐 벌써 답을 얘기해 줬잖아요. 미니멈 디스턴스라고. 왜? 가우시안이기 때문에 그런 거야. 그러면 가우시안일 때 어떻길래 그런 일이 생기는가 한번 보자 말이죠. 그래서 let's consider the optimum decision receiver. The receiver has received vector. 자, 이제 received vector, vector space에서 얘기하는 거예요. R이라는 vector is the result of demodulation. 어떻게 demodulation 한다고 그랬지? inner product 한다고 그랬지? 각 그 베이시스 벡터로. 그러면 각 디멘션의 코에피션트가 나오잖아. 그러면 이 코에피션트를 묶은 게 R이지, R 벡터. 그지? R 벡터, 그 다음에 보내진 벡터 SM, sent, 그지? 인덱스 M이 sent 된 거지. 그 다음에 노이즈가 add 됐지. 근데 노이즈는 몰라. 가우시안 노이즈야. 아는 건 뭐야? 분포밖에 몰라. mean and variance 알아. 그지? 그래서 mean and variance 알아가지고 멀티베리에이트 가우시안을 만들어요. 그러면 이 멀티베리에이트 가우시안 펑션이 이렇게 생겼다고. 그지? 그냥 그 원 디멘셔널 가우시안 노이즈를 숫자만큼 프로덕트 하면 이게 나와요. 오케이? 그리고 내 노트에 서플멘트 노트에 보면 그게 나오는데 한번 써보면 이건 써볼 만하니까 한번 써보면 이렇게 생긴 거지. 써보면 이런 식으로 생겼어. probability distribution n. n은 이런 모양이지. n1, n2. 3개까지만 할게. 그냥 아무리 길어도 똑같은 형태니까, 그지? 그러면 이 확률은 1 over square root of 2pi 하고, 그러니까 요거를 이렇게